Alright, example 3. This is by far the most fun problem in these notes. Gotta save the best for last, right? So, it says find the volume of the solid created when the region bounded by y equals x and y equals x squared minus 2x, so we're going to graph these, is rotated around the line y equals 4. So now we're not rotating around an axis, we're actually rotating around y equals 4. Remember, y equals 4 is a horizontal line. It's parallel to the x-axis. So everything's still going to be in terms of x here, but we have to think about what our radius is going to be. So we'll get a sketch here of that in just a second. Hint, what expression represents your inner and outer radii in this scenario? So remember, this is going to have, it's got two curves here. So probably this is going to be probably going to create some type of ring. This is if I was looking at it, if the axis was like right here, or the y equals 4 line went straight through here. So since it's going to create some type of ring, remember you have your little r and you have your big R. And so remember the formula for that would be pi, I'm just factoring out the pi, r squared minus r squared. And that's, I mean, the way of thinking about that is that you just take the area of the big circle, subtract the area of the small circle, and I just factored out the pi here. So we'll come back to this idea later. First we have to kind of get a look at the graph. So I'm going to zoom in here so I have plenty of space. And let's try to make this kind of as detailed as possible here. I already kind of know what the graph's supposed to look like, so that helps. But let's go ahead and put in our units here. So 1, 2, 3, 4. And about the same distance, 1, 2, 3, 4. And so our line, y equals 4, that we're going to rotate around, that's this line. And then the other line, y equals x, I'll try and do the two graphs in red, would look something like, trying to be as precise as possible here, it's going to look something like that. So there's y equals x, and then the other graph that we're going to do here is x squared minus 2x. So let's see if I can do that in like maybe green here. So x squared minus 2x, just so you know, that has zeros. Let's write it right here. So if I had y equals x squared minus 2x, if you were to factor this thing, you could see you'd have a 0 at 0 and at 2. So this graph kind of looks like it's going to hit there and there, and the vertex is actually going to be down here. Now this is, I'm just familiar with parabolas. If you didn't know that, you could just plug in points. I mean, you could plug in a 0, you get a 0, you could plug in a 1, you get a -1, plug in a 2, and so on. So when you plug this thing in, you get something like that. And actually, you could figure out where it's going to intersect, because if you plug in a 3, 3 squared is 9, and 2 times 3 is 6, so 9 minus 3 is 6. So it's actually, at 3, it's going to hit 3, so it's right here. And so we could see where it's going to intersect our graph. And that's really all we care about here, because we are trying to find what happens when we rotate this region around this curve. And so sure enough, there's going to be a gap here in the middle. So yes, this is going to create a washer scenario here. So we're going to find the area of an infinite amount of washers, add them all up, and that's going to be our volume. So let's see what it would look like. We could kind of sketch kind of what this would look like if we were to reflect everything. Again, this is just a rough sketch, right? If we were to reflect that line over the y equals 4, it would look like that. If we reflect the parabola, look something like that. I know it's not perfect, and then you could kind of fill in the gaps here, right? So like it creates some like cone shape here in the center, and then you'd have this weird shape down the center of down here. You'd have like some like hole in here, right? You'd have some empty space, and meanwhile you'd have this weird solid protruding from on the sides here. So we got this awkward shape. we're going to find the volume of this thing. So sorry you had to bear with my drawings once again. Hopefully some of you guys can make a better sketch. But the point here is we have two radiuses going on. So let's talk about those two radiuses. I'm going to do the first one in red, and that's going to be our small radius because that's our inner radius, and that's this distance, right, from to the red line, from the blue to the red line. So let's call that little r. Well, wouldn't that distance just be 4 minus whatever the height of this function is? So 4 minus that function, well, that function is just x, y equals x. So this radius is 4 minus x. All right, and the other radius, which I'm going to do in green, I know my drawings gets a little messy here, is from the blue line to the outer part of this green line. And so that's my big radius, and that's going to be 4 minus this function height, and this function height is defined here. So it's 4 minus x squared minus 2x. Since you're subtracting the whole thing, you're going to need to distribute these negatives, so it'd be a negative x squared and a positive 2x. So you got your two radii now. Remember, so that was the first step. Come up with, just kind of sketch it out, and then get your kind of equations for your radius. Now let's think about what the area of this thing would be. Well, we kind of already did that. It would be this, right? So let's plug in our information for our formula. It would be pi, and I'll try and color code it here for you still. I guess maybe I could have used blue. I'm going to use blue just because I think it shows up better. So let's just change this to blue. So our big R here would be 4 minus x squared plus 2x squared, and then minus my little r is 4 minus x squared. Okay, so this is the area of a washer, of one slice, you could say, here. Okay, now we need to find the area of all of these things from when? Well, it looks like from 0 to when it intersects here at 3, because that's where this region is bounded by, from 0 to 3. So what would that look like? That would look like this exact same equation. Let's put the pi outside. 0 to 3 of 4 minus x squared plus 2x squared minus 4 minus x squared. Let's put some brackets in here because we need to put our dx there. Boom. So that's how we're going to find the volume of all of those slices. Now we have the equation, simple enough, but the algebra here is pretty intense. So I'm going to ask you guys to pause and just try to work this out. Do a big box method here, do a box method here, and see if you can come up with what this should be, just kind of by multiplying this out, and you'll come up with one long equation. I'm going to pause the video, do the work, and then unpause it so we don't spend a bunch of time just watching me do some algebra. Okay, so if you use the box method, you get the 3 by 3 box here, you end up with this expression, and then box method here, you end up with this expression. Distribute the negative, you get this, and then finally when you simplify it all out, this is your expression that you're going to take the integral of. I have not taken the integral yet, but now that it's all simplified in polynomial standard form, we can take the integral pretty easily. So let's go ahead and do that. This would equal pi. Let's do our bracket. X to the fourth becomes x to the fifth divided by 5. Minus x to the third becomes x to the fourth, and then the 4 divided by the new 4 becomes 1, so we don't really need to write it. Minus x squared becomes x cubed, and that's 5 over 3, plus 24. The x becomes x squared, and 24 divided by 2 is 12. And we're going to evaluate this thing from 0 to 3. So one of the things you could recognize right away, if you were to plug a 0 into all these terms, you would just get 0. So all we really have to do now is plug in the 3. And hopefully you're following along or just doing this on your own, because from here on it's just some algebra again. So I'm going to go ahead and have you guys pause it again, and I'll just simplify this out, and then we'll unpause the video and check your work. Okay, so once we do the antiderivative, we plug in the 3, then it's just about simplifying it down. And you do have to get some common denominators here at the end, but you end up with 153 pi over 5. Just so you know, I've done this problem twice and on the calculator once just to verify this answer is correct, and it is. So let's kind of zoom out. Let's kind of go over this one more time. First thing we did is we did a sketch, and then we created a generic formula for the area of just one slice of this three-dimensional figure. Then we had to do some algebra, or more just some multiplying trinomials and binomials to get one expression so that we can take the antiderivative, because this isn't really something you could take the antiderivative very easily, right? This is like maybe if you did use substitution or something, but this gets pretty nasty pretty fast. So you got to simplify it all out to one polynomial expression, take the antiderivative, and then just simplify it out. And these are the steps, this step from here to here, and this step from here to here is what takes up a lot of time. But you can do it. And that's why a lot of times on the AP exam you're going to see, once you get to, like, say, this expression, that might be all they really need on an AP question, because they just want to see that you can set up the process, and they may not care so much about the algebra or that you can do the power rule correctly, right? Like, that should be some pretty basic stuff. So anyway, fun question. I'll see you guys in class. Thanks for paying attention to all that very long problems.